All right, this section or lecture will be about 5.4. What's kind of weird is the way they introduced this is 5.4 is called the indefinite integral, and we've actually talked about that a lot already. So this section actually has indefinite integrals and it has definite integrals as well. So really what I'm gonna do is I'm just gonna work out more integral problems. That's all. Both indefinite and definite. Remember, indefinite integrals had no limits, right? Indefinite was, oh, we just had this integral with no limits of f of x dx. And then when you integrated it, you got big f of x plus c, right? Remember, c means a constant because remember, there's an infinite amount of antiderivatives or integrals if you don't have any limits. Because again, how can we check the work? If you take the derivative of the right side, you should get to the left side right here when you have an indefinite integral. And then with definites, though, that's where we had limits, right? Like you say, oh, we're integrating from a to b of f of x dx. And this was big F, right? The antiderivative of F evaluated at B minus the antiderivative of F evaluated at A, right? And we would sit there and crank it out and get some kind of value. So this section, even though it is titled indefinite integrals, it has both. So I'm just going to, again, work out various kinds, all right? Mainly the more trickier ones, okay? Like trig functions, for example, because that's what always gives people problems, trig. All right, so here we go, right? Theta minus cosecant of theta, cotangent of theta d theta. Now, if y'all remember how I said with integration or finding antiderivatives, if it is separated by addition or subtraction, we can work them out individually, right? So I can say, oh, the antiderivative of theta minus the antiderivative of this chunk right here, right? Of this cosecant theta, cotangent of theta. But if it was just multiplication, you can't split it, right? Like I can't say, oh, this is equal to theta, the integral of theta minus the integral of cosecant theta times the integral of cotangent of theta, right? Remember, you cannot split it integrals when stuff is connected by multiplication or division. So remember this, if you have the integral of AB, you cannot say it's the integral of A times the integral of B. That's illegal. Same thing with division. We cannot say, oh, that's the integral of A over the integral of B, okay? There's other techniques that we're going to talk about later on that will let us deal with that right there. So you cannot split that right there. So in this case right here, we could say, oh, this is the integral of theta minus the integral of cosecant of theta cotangent of theta d theta. Well, this one's not too bad, right? It's just, I'm reading my d theta. This is just the power rule right here. So this is 1/2 theta squared. What about this trig function right here, or this right here? Well, with the trig functions, remember, a lot of these are just come down to memorization. Like there's an antiderivative of cosecant theta, cotangent of theta. It's negative cosecant of theta, okay? So this, all this right here, the antiderivative of that is just a negative cosecant of theta. And then don't forget, since we don't have limits, we're going to have a plus c. Make sure it's an uppercase C when you type it into WebAssign. And then to finish it off, it's just 1/2 theta squared plus cosecant of theta plus c, just like that. Let's try this now. We'll try another indefinite integral. So secant of t times secant of t plus tan of t dt. So again, we can't say this is the integral of secant of t times the integral of secant t plus tan t. We can't split it up because since it's multiplication. So what do we need to do? Let's get rid of the multiplication. How are we gonna do that? Let's distribute. If we distribute the secant t, right, this into this and that, what do we get? We get secant squared of t plus secant t tan of t. I'll do this dt. So now with these actually are nice antiderivatives, right? Remember with the trig functions, or really any function, when you're finding its antiderivative, you're trying to think of something where if you take its derivative, it would bounce you back to your initial expression. So you could think, what trig function can I take the derivative of that's going to get me back to secant squared? It's tangent. Remember, the derivative of tangent is secant squared, so that's done. What about this one? Is there something where if I take the derivative of some kind of trig function, it's going to bounce me back to a secant tangent? Yeah, it's actually secant. The derivative of secant is secant tangent. The derivative of tangent is secant squared. Remember, when you have indefinite integrals, you can check your answer, because if you take the derivative of the antiderivative, you should get back to your initial function. And then last but not least, don't forget the plus c, right? Because we have a indefinite integral or something without limits. Let's try this now. So now we have limits, right? So this is a definite integral, but we still work it out the same way. What's the antiderivative of e to the x? This constant, you just bring it along, right? We just bring it along. But what's the antiderivative of e to the x? It's e to the x, right? How can you check that? Well, what's the derivative of e to the x? It's e to the x. Remember, if I take the derivative of my antiderivative, I should get back to my initial function, which I do. And then this time we're evaluating from natural log of 7 to natural log of 3. What does that look like? Well, that's going to be 2. And then remember, we're going to have the upper limit. So that's e to the ln of 7 minus e to the ln of 3. If you wanted, you could have said 2e ln 7 minus 2e ln 3. It's the same thing. Okay. So now as far as simplifying, remember, e is a number, right? Ln of 7 is a number. These are all finite numbers right here. But only simplify if something nice comes out of it, and something nice does come out of this right here. Remember, e to the ln of stuff is just the stuff. E raised to the ln, they undo each other, and you're left with what's on the inside. So this is actually 2 and then 7 minus 3. If you type e raised to the ln of 7 in your calculator and hit enter, it's going to spit 7 out for you, okay? So then we can keep going, right? This is 4 times 2, and your answer is 8 in this instance. So remember, no decimal answers, only simplify if something nice comes out of it. In this case, don't forget that, right? That came from Math 130, right there at college algebra. Now, what if we have this? So very complicated looking function, right? And I put a root. Now it's even worse. But with these right here, remember, if you have a constant over the sum of squares or difference of squares in some kind of root, that's usually some kind of arc trig function. Remember, if we have the integral of 1 over the square root of 1 minus x squared dx, that's equal to arc sine of x plus c. And really important, the range, that's the y values, falls between negative pi over 2 and pi over 2. That's important now, and I'll explain why in a second. But if we go out there and integrate this one, this 5, don't say, well, this 5 is not the one. I don't know what to do. No, you can pull that 5 out, right? If I pull the 5 out, now you have the arc sine, right? It's the same thing right here. Did you have to pull the 5 out? No, you could have just left it like that. And you could have said, oh, well, this is 5 arc sine of x evaluated from 1 to 1/2, like that. So how do we do this, right? Well, you could try to plug it into your calculator, but you may wind up with decimal answers. You probably will. All right, so how do you figure out arc sines of values? It's the reverse situation of like if you had sine, right? Like we're not being asked what sine of 1 is. We're being asked what type of radian value would give us a sine value of 1. Okay, what type of radian value? When I say radian, that's stuff like your answer when you're talking about arc sine, cosine, arc tangent. Those answers involve something like pi. Okay, like 0, pi over 6, pi over 4, pi over 3, 2 pi over 3, 5 pi over 6, those things, for example. What's really important though is let's come back to this range right here. So when they say, oh, the range is from negative pi over 2 to pi over 2, what are they talking about? They're only talking about this amount right here. So pi over 2 is, remember, when it's positive, you rotate clockwise. I'm sorry, counterclockwise. When it's negative, you rotate counterclockwise. So this is negative pi over 2. It's really important to remember that your answers can only lie in quadrants 1 or 4. Why? Because with trig functions, usually there's 2 answers all the time that can satisfy some kind of answer, right? Or some kind of solution. But by the range being it's solely delegated to these 2 quadrants, you're only going to wind up with 1 answer. So now we need to figure out arc sine of 1. What does that mean? Well, we're trying to figure out which one of these y values, because remember, when we talk about points on the unit circle or any kind of graph, it's always x and y, right? Remember, the cosines were the x's. You had x and y. And this was the cosine. And the y was usually the sine, right? So you need to figure out which one of these y values on this unit circle in the blue has a y value of 1. Which one is it? It's this, right? At pi over 2, what is the point right there? It's 0, comma 1. So again, arc sine of 1, you're basically asking for which one of these values on the unit circle amongst this blue semicircle right here is going to have a y value of 1. So it would be pi over 2. That is what your answer would be. So that's what arc sine of 1 is. If they asked you what's arc cosine of 0, for example, you'd have to ask yourself which one of these points along here has an x value of 0 if they ask for arc cosine. And that would also be pi over 2. Now, what about arc sine of 1/2? So now what you need to do is you need to look along this unit circle and ask yourself which one of the y values with those points is going to have a y value of 1/2. Well, where is it, right? How do we figure that out? I'm just going to make this a little bigger. Remember, we're stuck between here and here, right? This is pi over 2, negative pi over 2. And we have stuff in between, right? Like you have this, this, and this. There's some nice points right here, right? Remember, what were they? Like this one, this pi over 4 was square root of 2 over 2. And this is square root of 2 over 2. And then what about this one right here? This was square root of 3 over 2. And this was 1/2. And this one right here, was what? This was 1/2 and then square root of 3 over 2. So the easy way to remember it is start up here and go 1, 2, 3, and then you can put a root, right? We could put a root right here if we wanted to. Square root of 1 still 1. So you go 1, 2, 3, and then 3, 2, 1, just like that. And what are these in terms of pi, right? Like this is pi over 6. This is pi over 4. This is pi over 3. And of course, this up here is pi over 2. So now arcsine of 1/2 is asking which one of these y values has a value of 1/2. Y values, right? It's this one. What's that in terms of radians? It's pi over 6. So this is minus pi over 6. If you typed an arcsine of 1/2 into your calculator, it's going to give you some weird decimal answer because it's dividing pi divided by 6 and spitting that out. But again, you're going in the reverse direction. Whatever trig function this is, whether it's sine or cosine or a mixture of the two, you need to look at those respective points and figure out which one gives you that right there. If they ask you what's arc cosine of 1/2, like if they said, what's arc cosine of 1/2? What's that equal to? Well, then you have to look at the x values. Why? Because cosine's x. You have to look at the x values and determine which one of those is giving you 1/2. Oh, it's this one, because that's x. Remember, x deals with cosine. What's the radian value? Pi over 3 right there. That's how that works. And then we keep going, right? Because this is just 5, and then this is, if we combine these, right, this is 3 pi over 6, this is 2 pi over 6, which is 10 pi over 6, which reduces to 5 pi over 3. Again, no decimals, right? Leave your answer in exact form. Let's try another arc function. So I'm going to leave that unit circle up because it's still important. Let's look at this one. So we have 1 over square root of 3 to 1 of 2 over 1 plus x squared dx. So again, when you see a constant over, the sum of squares, the difference of squares inside a root or something like that, you're dealing with some kind of arc trig function. In this case right here, this is an important one that comes up a lot. The integral of 1 over 1 plus x squared dx is just arctan of x and then plus c. So remember with that 2, you're just going to slap it out in the front, right? So this is 2 arctan of x. Just like how with the previous problem, I pulled out the 5, right? And we had 1 over square root of 1 minus x squared. I just multiply the 5 back in. It's literally the same thing right here. But this time, we're going to evaluate from 1 to 1 over the square root of 3. And the range is the same as arcsine, okay? The range is still from negative pi over 2 to positive pi over 2. So again, we're defined to this area right here. Now, how do we work this out? Because this is saying, oh, 2 arctan of 1 minus arctan of 1 over square root of 3. How do we do that right there? Again, it's going to be very similar to the last one. We're looking for which one of these points is going to give us a 1, like x and y values. But maybe one, or which one of these points is going to give us 1 over square root of 3. Now with arctangent, it's a little different, right? Remember, tangent is sine over cosine. So you need to be thinking the ratio y over x. Remember, tangent is y over x. You need to be asking yourself, okay, well, which one of these points, when I divide the y value over the x value, will be equal to 1? It's pi over 4. Why? Because what's square root of 2 over square root of 2? It's 1. So again, what did I do? Remember, for the arctangents, you have to think in terms of ratios of y over x. You need to ask yourself, which one of these points somewhere on the unit circle, when I divide the y over the x, will give me this inside piece right here? So which one of these 3 points is going to give me a positive 1 when I divide the y over the x. It's the middle one right here. It's pi over 4. Now, what about arctan of 1 over the square root of 3? So this one, it's a little more tricky, right? But again, we're still thinking which one of these, when I divide y over x, is going to give me 1 over the square root of 3. So let's look at, so remember at pi over 6, that point was square root of 3 over 2 over 1/2. If I do y over x, remember this is x and y, what do I get? We're just checking right here. So this is 1/2 divided by square root of 3 over 2. That's the same thing as saying 1/2 times 2 over the square root of 3. Well, these 2's get knocked out, so you get 1 over root 3. So we discovered the correct radian value. So arctangent of 1 over root 3 is actually pi over 6. Y'all see how I did that right there? Again, I was just dividing the y over the x. If that one didn't work and give me 1 over the square root of 3, it can't be this one because we just saw root 2 over 2 over root 2 over 2 is 1. So then you try the other one like that, right? Be very careful about the order. Remember, tangents y over x. Again, with the arctangent, what are you doing? You're looking for the ratio of which y over x value, which y over x. I keep saying y over x because people are going to do x over y. No, it's y over x. When you divide y over x, is it going to give you this inner value right here? But that's for the arctangent. That's what you're looking for. So we figure that out. We can do like terms again. So this is 3 pi over 12 minus 2 pi over 12, right? I'm just doing LCD. And then this is basically 3 pi over 12 minus 2 pi over 12 is pi over 12 times this 2. We get 2 pi over 12, which is pi over 6. So again, take your time with these arc trig functions. If you don't know how to find arc trig stuff, go back and practice those problems, right? Everyone should be familiar with arc trig functions and trig functions in general because you had to take trig or pre-calculus as a prerequisite for this course. All right, now we have 0 to 1, or we're integrating from 0 to 1 of 5x minus 5 raised to the x dx. So algebraic expression, exponential expression, right? Because the x is in the exponent. So this one's not too bad, but how do we integrate this? Well, remember, you have this generic form. If we have the integral of a to the x dx, that's just a to the x over natural log of a plus c. Okay, so with this, the antiderivative or integral of 5x is just 5/2 x squared, not an issue, minus this one, if we follow it, a is 5, right? So it's going to be 5 to the x over ln of 5. No plus c though, right? Because we have these limits right here. So let's plug it in. So we're going to have 5/2 and then 1 squared minus 5 to the first over ln of 5 minus the entire bottom limit, right? Make sure you put parentheses or brackets or whatever to signify, oh, we're subtracting that entire quantity. So we have 5/2 times 0 squared minus 5 to the 0 over ln of 5. So what happens right here? Well, this is just 5/2. This stays as 5 over ln of 5. Do not convert this to a decimal unless something nice comes out. Guess what? ln of 5 doesn't give you something nice. How do you know? Plug it into your calculator. You're going to get a decimal, so leave it like that. Now we have minus. Well, this becomes a 0. This does not become 0, right? Why? Because what's 5 to the 0th power? It's not 0, it's 1. So this is 1 over ln of 5. So then what do we ultimately have? We have 5/2 minus 5 ln of 5. And then a negative times a negative is a positive, so you have plus 1 over ln of 5. And we can combine these, right? Because look, like terms, denominators are the same. So you have ultimately 5 halves minus 4 over ln of 5. Again, leave it in an exact form unless something nice comes out. You'll know if something nice comes out because if you plug into your calculator and it spits out a nice answer, like an integer that's like a positive or negative whole number, then that's fine. But otherwise, leave it in its exact form. All right, so we have the indefinite integral of 1 plus tangent squared of alpha d alpha. Okay, so integrating one's not a problem, but how will we integrate tangent squared of alpha? That's a little more tricky, right? Why? Because again, you could try to think what's a function that I could take its derivative of that's going to bounce me back to tangent squared. Well, there is nothing that necessarily does that. So then what you have to start thinking is, oh, is there another way I can rewrite this? Like maybe you could break it down into sine or cosine, or you can use some other trig identities. Remember, you have sine squared, and I'll say x plus cosine squared x equals 1, right? That's a familiar function that people know about. What if I took this thing and I divided it by everything by sine squared? What would happen? What's sine squared over sine squared? 1 plus what's cosine squared over sine squared? That's cotangent squared of x equals what's 1 over sine squared? That's cosecant squared of x. That's another trig identity that you all have probably seen, or you should know because it's useful. And there's another one. What if I take, again, the sine squared plus cosine squared of x equals 1, and I divide everything by cosine squared this time? What do you get? What's sine squared over cosine squared? That's tangent squared. What's cosine over cosine? 1. What's 1 over cosine squared? That is secant squared of x. Well, look at that. Tan squared plus 1. Tan squared plus 1. Order doesn't matter for addition, right? So we could say, hey, this all is just equal to secant squared of x dx. Why do we do that? Because the antiderivative of secant squared is something nice, right? What's a function that we can take its derivative of that bounces back to secant squared? It's tangent. So we get just tan of x plus c. So again, these three trig identities are very important. This one, and this one, right? 1, 2, 3. But if you're like, I can't remember all three, all you have to do is remember the first one. We all know sine squared plus cosine squared equals 1. How did I get the other two? Remember, I just took one case where I divided everything by sine squared and simplified it. And then I went back to the original, sine squared plus cosine squared, divided by cosine squared, and that gave me another one. So as long as you remember the first one, you can derive the other two, right? You just divide everything by the same trig function, the squared version, and it's always going to spit that out. So be on the lookout for, can we rearrange trig identity or trig functions in other ways? And you definitely can. That's always a very useful trick. All right, what about this right here? 0 to pi over 3, and then we have sine of theta plus sine of theta tan squared of theta over secant squared of theta. So remember, this we have a division problem right here. We can't just go, oh, the integral of the top divided by the integral of the bottom. No. So we have to think, how can we manipulate this right here? Remember when you were trying to manipulate rational expressions, right? That was like polynomials over polynomials. You try to factor something, right? Just to see what happens. Can you factor something right here? You absolutely can, right? Look at up top. What do they share? What does the numerator share up top? A sign. If you factor out a sign, what's left over? 1 plus tangent squared of theta. And the bottom has not changed yet. And we have this d theta. Now, something familiar just popped up. What happened? What's 1 plus tangent squared? What did we just see that it was? It's secant squared, right? So now we could say, oh, this is from 0 to pi over 3 of sine of theta. And then secant squared of theta over secant squared of theta. Remember, all this became this, right? We just saw it right here, right? And then something even better happens. More things cancel, right? Look at that. These go. So now we just have the integral of sine of theta d theta. And you're evaluating it from 0 to pi over 3. Well, this is very straightforward, right? Because remember, the antiderivative of sine of theta is negative cosine of theta. Remember, if I take the derivative of negative cosine, what do I get? Positive sine, right? Because derivative of cosine is negative sine, but with the negative out in the front, you get a double negative, which makes it a positive right here. Don't forget that right there. Now, we can evaluate. We have negative and then cosine of pi over 3 minus cosine of 0. So what happens right there? We have negative. What's cosine of pi over 3? That's the square root of 3 over 2. What's cosine of 0? That is 1, like that. So what do you wind up with? You wind up with basically 1 minus the square root of 3 over 2. So I basically multiplied the negative, and negative times root 3 over 2 is right here. Negative times negative 1 is 1. So that is your answer. Again, leave it in root form. Do not sit there and change the answer, okay, into decimal, unless it asks you to do that, which it won't. All right, let's check this one out. So you have roots, right? Well, what do you want to do with roots when you're deriving or taking the antiderivative? Convert them into exponential form, right? This is 0 to 1. This is x times x to the 1/3 plus, actually, leave it like this. This is put parentheses around that. And then x times x to the 1/4 power dx. So remember, these are x's to the first. So what can we do? Remember, when you have same bases and you're multiplying, you add the exponents. This is x to the 4/3. This is x to the, what is that? 5/4 dx. We still haven't taken the antiderivative yet. We're just combining like terms right here. All right, so now let us go out there and take the antiderivative. So remember, it's the power rule, right? It's x to the n plus 1 over n plus 1. This becomes x to the 7/3 over 7/3 plus x to the 9/4 over 9/4. And we're evaluating that from 1 to 0. Remember though, when you have these fractions over fractions, this is the same thing as taking a denominator and multiplying by the reciprocal, right? So this is actually 3/7. I don't need this. X to the 7/3 plus 4/9, X to the 9/4, evaluated from 1 to 0. Let's go out there and plug these values in. So remember, it's the upper limit minus the entire bottom limit. Don't forget those parentheses. Now what's nice is this whole second term zeroes out, right? Because it's 0, 0 right here. What's 1 to the 7/3? That's 1. What's 1 to the 9/4? That's 1. But when you take that times their coefficients, right, we get 3/7 plus 4/9, right? And then you wind up with 56 over 63. So there's your final answer right there. So again, don't forget, I did this one again to remind you all that whenever you have radicals, right? Radicals, that's like root stuff, convert them into exponential form as you're working them out. All right, so let's try one more here. So right here, we're taking the integral or antiderivative of an absolute value function. Now, you don't have any like this on your homework or anything like that, but I'm just doing it because it is going to pop up at some point and you have to know how to deal with it. Now, remember, we dealt with this when we were finding limits, right? Remember what happened when we had to find the limits with absolute values? We had to break them up into two linear functions, right? Because that's what absolute value functions are. They're always V-shaped, but it's basically a piecewise function. So absolute value of x minus 2, it will look something like this. It's just a V that's shifted 2 spaces to the right from the origin. And both of these straight lines they are opposite equations, right? So remember the trick was with the limits, the right hand piece was always this, just dropping the absolute value. So this is x minus 2 right here. The other piece, the left piece, was the opposite of this one. So the opposite of x minus 2, remember the trick was you just slap a negative sign out in front of it right there. Now, how does that affect our problem? Well, we're going to break it up, right? Remember, we were asked to find the area from -3 to 4. So we want, when you find the integral of something, you're finding the area under the curve. So we want this stuff, and we're looking for this stuff right here. So we're going to have two different integrals with two different limits and two different functions. So how are we going to find the area of the purple stuff? Well, the purple stuff is going to go from -3 to 2 of negative x minus 2 dx. And then the area of the blue stuff is going to start from 2 and it's going to go to 4 because remember it ends at 4. And then we're going to have x minus 2 dx. So remember the trick is you got to break it up into two smaller functions. The piece off to the right, shooting off to the right side, whether it's up or down, is your initial function. You just drop the bars. The other segment or other half is just the opposite. The opposite is you slap a negative in front of the whole entire function, but you just drop the bars. So now let's go out there and work this out, right? So if you want, you can distribute the negative in first. This is negative x plus 2 dx. This is 2 to 4. This is 2 to 4 of just x minus 2 dx. And then we're just going to go out there and integrate and evaluate. So this is negative 1/2 x squared plus 2x evaluated from 2 to negative 3. And then we're going to have plus 1/2 x squared minus 2x evaluate from 4 to 2. So be very careful, right? The limits are different right here. So we're going to have negative 1/2 2 squared plus 2 times 2 minus, and then we're going to plug the negative 3 in. This is negative 1/2 negative 3 squared plus 2 times negative 3. So that's just this chunk right here. And then now we need to do this one, right? So I'm going to do this in red right here. So this is 1/2, and then we have 4 squared minus 2 times 4 minus its respective bottom limit. So we're going to have 1/2, and then 2 squared minus 2 times 2. So let's work all this stuff out right here. Let's see what happens. So 2 squared is 4 times the negative 2 is a negative 2. And then plus 4, right? And then we have minus. I'm still going to keep these parentheses right here. So that's 9 times a negative 1/2 is negative 9/2. And then we get minus 6. So that's done. Remember, got to do that first. Negative times negative is a positive, times a negative is a negative. Now let's go on to the red stuff. This is plus 4 squared is 16. Half of 16 is 8 minus 8. And then minus, I'm going to keep the parentheses right here. What do we have? 2 squared is 4. Half of 4 is 2. Then we have minus 4 right there. So what do we come up with? Negative 2 plus 4 is 2 minus negative 9/2 minus 6. So that's like saying negative 9 over 2 minus 12 over 2. So you get negative 21/2. These cancel out. Then we get minus. This is a negative 2 right here. So now we have what? We have 2 plus 21/2 plus another 2. That gives you 4 plus 21/2. And then this is 8/2 plus 21/2, and that gives you 29/2. So that would be your final answer right there. Remember, with absolute value, whenever you're integrating, you always want to break it up into two functions, right? And the functions are basically going to be opposites of each other. So remember, when you break it up, though, whether it's something like this or like this, the right piece is the right, right, left, and left. The right piece is always just the initial function, right? You drop the absolute value bars. The left piece is the reverse of that. You're going to throw a negative in front of that absolute value right there. So again, this is just more practice problems. It's important that you remember the antiderivative of those trig functions. And for the arc ones as well, those do come up, especially the arc tangent, okay? So make sure y'all commit those to memory. What you can do is just take a sheet of paper and just write them down over and over, right? Like maybe 10 times or something, and eventually it'll just get fused into your head, okay? So that concludes this section.